Up to this point, we have already discussed Schrödinger's wave equation and the physical meaning of the wave function. In particular, we introduced the Born interpretation, namely that the squared magnitude of a wave function is interpreted as a probability density. Once that interpretation is accepted, the next question becomes unavoidable. If the squared magnitude of the wave function represents a probability density, then what restrictions must the wave function satisfy in order to be physically meaningful? That question leads us directly to the next topic on this roadmap, normalization. And why is normalization so important? Because if a single particle exists somewhere in space, then the total probability of finding that particle somewhere must be exactly 1, not 0.8, not 1.3, but exactly 1. In other words, the wave function cannot merely be any mathematical solution of Schrödinger's equation. It must also satisfy a probabilistic requirement. So this part of the chapter is not just a mathematical technicality. It is really about making sure that the wave function can be connected consistently to physical reality. So you can think of it this way. Schrödinger's equation tells us what kinds of functions are mathematically allowed as solutions, but normalization tells us which of those solutions are physically interpretable as states of a single particle. So in the next few slides, we will do 3 things. First, we will define what normalization means. Second, we will discuss which kinds of solutions are not normalizable and therefore must be rejected if we want an ordinary single particle probability interpretation. And third, we will address an important conceptual question. If a wave function is normalized at one instant, how do we know it stays normalized as time passes? That last question is particularly important because probability conservation must hold at all times, not just initially. So let's now begin with the definition of normalization. Now we come to the definition of normalization. Since the squared magnitude of the wave function represents the probability density for finding the particle at position r and at time t, then for a single particle, the total probability of finding it somewhere in all space must be equal to 1. Therefore, we require the expression shown here. This is the normalization condition. In Cartesian coordinates, this can be written more explicitly as shown. This equation expresses a very simple physical idea. If the particle exists, then when we search over all space, the probability of finding it somewhere must be 100%. On the other hand, if psi of r and t is a solution to the Schrödinger's equation, so is a times psi of t, where a is any complex constant. This happens because Schrödinger's equation is linear. If you multiply a solution by a constant, it remains a solution. Mathematically, that is straightforward, but physically it is very important because it means the overall amplitude of the wave function is not fixed by the differential equation alone. So what do we do with that freedom? We use it to impose the normalization condition. That is exactly what normalization means. We choose the constant a so that the square of the magnitude of a times psi of r and t integrated over the whole space equals 1. Since the squared magnitude of a times psi can be written as shown, we can adjust the value of a so that the total integral becomes unity. This is why we emphasize here that every physically acceptable wave function can be normalized by multiplying it by an appropriate constant. Please note that this sentence doesn't say every mathematical function can be normalized. It says every physically acceptable wave function can be normalized. This means that the integral of the absolute magnitude of the wave function squared over space must at least be finite and non-zero. Otherwise, no choice of constant can fix it in the right way. So the main message of this page is the square magnitude of a wave function is a probability density. Therefore, its integral over all space must be 1 for a single particle. And because Schrödinger's equation is linear, we are free to multiply a solution by a constant. So we choose that constant so that the total probability becomes unity. That's the normalization procedure. Now that we have defined normalization, the next question is, what kinds of wave functions can actually be normalized? A function satisfying the normalization condition is said to be quadratically integrable, or more commonly square integrable. In other words, the integral of the squared magnitude of the function over all space must be finite, as given by this expression. Then after multiplying by a suitable constant, we can make that integral equal to 1. Functions with this property are called normalized functions once the normalization constant has been chosen. These are the kinds of functions that can represent physically meaningful single particle states in the ordinary probability interpretation. Then two types of solutions that must be rejected if we want a normalizable state. The first is the trivial solution, where psi of r and t is equal to 0. Mathematically, this certainly solves the Schrödinger equation in many cases, but physically it is useless. It corresponds to 0 probability density everywhere, so it cannot represent an actual particle. The second unacceptable type is a solution for which the normalization integral diverges, as given by this expression. If the integral is infinite, then no finite multiplicative constant can make it equal to 1. Such a function cannot be normalized in the usual sense, and so it cannot be interpreted as the probability amplitude of a localized single particle. That's why we say that only square integrable solutions have physical meanings. Now let me add an important remark here. In introductory quantum mechanics, this statement is usually represented in the context of bound states, where the wave function decays sufficiently fast at large distance. Later, in more advanced treatments, you will encounter plane waves and scattering states, which are not square integrable in the ordinary sense and must be treated using a generalized normalization procedure. But for the present chapter and for the standard single particle probability interpretation, square integrability is the key criteria. Now think about this question. Suppose the wave function is normalized at time t equals 0. How do we know it will remain normalized as time goes by? That is a crucial question. After all, if quantum mechanics is self-consistent, then the integral of the squared magnitude of a wave function over whole space that represents total probability 1 at an initial time should continue to represent total probability 1 at later times, as long as the system evolves according to Schrödinger's equation. So to show this, we consider the one-dimensional case for simplicity. The idea is the same in 3 dimensions, but the algebra is cleaner in 1 dimension. We start with the normalization integral and differentiate it with respect to time. So the question reduces to computing the partial time derivative of the square of the absolute magnitude of the wave function psi. Since the squared magnitude of psi equals psi times its complex conjugate, we apply the product rule. We end up with the expression shown here. This is the key starting point. Next, we use the Schrödinger equation and its complex conjugate to replace the time derivatives. The one-dimensional time-dependent Schrödinger equation is shown here. Rearranging it gives the expression as shown. Now take the complex conjugate of this expression. Assuming the potential V is real, we obtain the expression shown here. These two expressions are then substituted into the product rule formula. We end up with the expression shown here at the bottom of this page. We see that the potential terms cancel each other. This cancellation is very important because it shows that the time variation of the total probability is not caused directly by the potential term. Now let's continue the algebra from the previous slide. After the cancellation of the potential terms, what remains is this expression, which may look a bit awkward at first, but it can be rewritten as a total derivative with respect to x as shown. So the time derivative of the probability density becomes a spatial derivative of another quantity, and that quantity now is within the square brackets. Now integrate both sides over OX. The integral of a total derivative of the probability density function becomes a boundary term shown here. Using the physically acceptable boundary condition in which the wave function approaches 0 as x approaches plus minus infinity, we see that the right-hand side of this expression must vanish. Note that the boundary condition here means the boundary contribution vanishes for a normalizable bound state wave function. And this is the central result. The normalization integral must be time independent since the probability of finding the particle somewhere in space must be unity at all times. In other words, if the wave function is normalized once, it remains normalized throughout its time evolution, provided it obeys Schrödinger's equation and satisfies the appropriate boundary behavior. This is exactly what physical consistency requires.